Chapter 1B, Displaying Distributions with Graphs. We will study how we look at data through different types of graphs. We'll look at both categorical data, where we study categories, and numerical or quantitative data, where we study numbers. Read through the vocabulary. I will refer back to this vocabulary as we are working through the examples. Example 1 is a pie chart. Our first question to think about is, what's the source of this data and when was it gathered? So we're told here that the pie chart data comes from the LMC Office of Institutional Research, where they research LMC students and data about the college, and it's from 2009. So if we look over at the pie chart, we want to know who or what are the individuals that we're studying here. So the title of the pie chart is LMC's Ethnic Composition, Fall 2009. And then after that, we see in parentheses, N equals 11,056. So that's the number of students who were enrolled at LMC in fall 2009. And if we look at the values here on the pie chart, we see we've got the different ethnicity categories that students were given to choose from. One of the categories, unknown, you can think about that as declined estate. So what's the variable being measured? Well, they're asking students about their ethnicity, so that's the variable, the overarching category that we're studying. And then the values are the different choices that students were given to answer. So those are 2 or more races, unknown, which we can think of as declined estate, Caucasian, Hispanic, American Indian, Asian, Pacific Islander, African American, Filipino. So all the different ethnicity choices that were given to students in this survey. What type of variable is this? Well, ethnicity choices are not numerical, so this is categorical data. Anytime someone's taking a survey where they have different word answers to choose from, not giving a particular number, we know that's categorical. Even when the numbers are grouped together, we can think about that as categorical, because to be quantitative, you have to be able to take an average. And so here you definitely couldn't average the ethnicities to get a meaningful number or a meaningful category. So what are some of the questions that LMC might answer using this data? So we might want to know what ethnicity has the largest population at LMC. We might want to know how many different ethnicities are represented in LMC. We might want to know what percent of students are not Caucasian. Often this data is used by the research office to make sure that the students who come to the college are close to the proportions of people out in the community. And they like to check to make sure, is there a group that we are not reaching? Maybe we need to advertise more to certain communities or certain ethnicities that we've missed, letting them know about the college. So that's how this data is used by the college and the district. And we want to know, does this pie chart show the distribution of this variable? Why or why not? Well, if you notice, we see all possible choices here, right? They've included the declined estate or unknown category. If you check the percentages, they add up to 100%. Sometimes when you're adding a pie chart, you get like 99% or 101% due to rounding, but essentially this adds up to 100%. So we see that all possible answer choices are there for students. So we say this is a distribution, right? All possible ethnicity choices that students could have chosen are represented. So here's a 3D bar graph below. This is showing population distribution of the United States. So what's our variable here? Well, think about each different bar here is representing a city. This is called U.S. metropolitan population distribution. So metropolitan tells us they're looking at the big city areas. So our variable here is U.S. cities, since the population value is depending on which city is selected, right? If you're making your bar graph here, you'd think about the x-axis, this is 3D, but you think about the x-axis as representing the city names if you were going to shift to a 2D bar graph. So what are some of the values the variable takes on? Well, the different city names, right? We've got San Francisco, Los Angeles, New York, Boston, Santa Fe. The values are the cities in the U.S. And then the count is the population values. So the cities are categories. So this is what we think of as a categorical variable. And the bar graphs correspond with the categorical variables, right? So this bar over here looks like it's Los Angeles. Here's probably the San Francisco Bay Area. This might be Sacramento right here. Looks like we've got Seattle up here. Maybe this is Portland. I'm not quite sure. We can guess the tall graph, or the tall bar, is probably New York City. So the height of the bars in the key at right are listed in scientific notation. So this is a good reminder of scientific notation if you haven't seen it in a while. So notice one of the cities has this tall bar that is 1.5 E7. So they're counting the number of people in that city. So in scientific notation, E7 means move the decimal point 7 places larger. So if we think about it, 1.5 E7, if I move my decimal point 7 places larger, that's 15 million, or a 15 million population. So it looks like if we come back up to our bar chart that maybe New York or LA might be this tall height of 15 million. And they must be including, when they say metropolitan area, they must be including also surrounding cities and surrounding areas. So what do we notice about the population in the U.S. from studying this 3D bar graph? So we notice that the high population cities are clustered on the West Coast and the East Coast. If you come look up here, you see high population over here in California and high population in the East Coast. There's also some high population here along the Great Lakes. So I think this is probably, we've got Chicago over here and some other big cities in the Midwest. And the Midwest and Southwest have medium high population cities, not quite as large as New York or Los Angeles or San Francisco, but pretty high. And then the west and the central part of the U.S. over here does not have a lot of high population cities. So very interesting. Example 3 has the results from a Gallup poll. So we first want to think about the source of the data and when was it gathered. This is always our first question we want to think about. So here it was coming from Gallup Polling Agency, and this data is from 2001. So we see that the 1,000 adults who are 18 years or older, that was taken in April 2001. We see this as a randomly selected sample, so that tells us this is useful data. It's random. If it wasn't randomly selected, we know there might be biases. And then the sample of 501 teenagers was collected from March through May 2001, and the teenagers were ages 13 to 17. So the individuals are the people, in this case, who were surveyed. So it's the 1,000 adults and 501 teens from the United States. And then we want to think about, well, what are the variables being measured? So we've got two charts here from the survey. So the first chart here is self-description of health, where adults and teens rated themselves on a scale from excellent to poor to describe their health. And then the second chart is survey respondents were checking boxes about things they have done that are not good for their health. So the second chart we say is things that were done that were not good for the health. And then what are the values of each variable? So we can draw arrows up here. So for self-description of health, the value choices are excellent, good, just, fair, and poor. 4 choices there. And then over here for things that they have done that are not good for their health, we see a whole list of possible choices going from I weigh more than I should, I don't get enough sleep, I drink alcohol, I don't watch my diet, I don't get regular exercise, I don't get regular checkups, I smoke cigarettes. So we draw arrows to all of these values, the possible answer choices. So we agree these are categorical variables since the answer choices are categories, they're not numerical. And then only one of these sets of data makes sense to represent with a pie chart. So remember, a pie chart has to show the whole distribution and has to total 100%. So if we look at the first chart, self-description of health, both adults and teens total 100% in each column. So we could do a pie for adults and a pie for teens. But if we look at the things I've done that are not good for their health, people were allowed multiple check boxes here. So if you add up these percentages, these are more than 100%. And so you wouldn't be able to use a pie chart in this scenario. You could do a bar graph, you could do other ways of comparison, but you wouldn't put these in a pie chart because the total would be more than 100%. And if we wanted to draw a bar graph to compare adults and teens responses, should we use the counts here, the adult count and the teen count, or should we use the percents, the adult percent and the teen percent? Since there's a different total, there were 1,000 adults and 501 teens, we want to compare with percents so that we can interpret the difference. Anytime we compare different size groups, we need to convert to a percent or a proportion. You can think about a proportion as the fraction of the decimal. So we don't want to compare the count because, of course, 370 adults who don't watch their diet is more than 165 teens who don't watch their diet. But if we compare 165 out of 501, that's 33%. And 370 out of 1,000 is 37%. So when we look at the comparison, these values are closer as percents than we would think if we just looked at the number, because we've got different denominators here. The denominators for the teens are 501 teens surveyed. The denominators for the adults are 1,000. Example 4 is from Consumer Reports 2016. Consumer Reports is a magazine that reviews consumer products, including cars. And so we're looking at what brands make the best car. So our data source, we say, is the Consumer Reports magazine. It was gathered 2016. And then what's described in this chart? Well, they're looking at car brands, right? And they list the different makes. And then each make has a rating of an overall score, a road test score associated with driving the car, predicted reliability that corresponds with these circles. And so we see the circles go from better to average to worse. And then a percent recommended of the models. So for example, Audi, 100% of the models were recommended, but its reliability here, if we come match, that's not quite the best reliability. So these are different variables that we went through that are being measured. So the overall score, that's a quantitative or numerical variable. The road test score is quantitative or numerical. The predicted reliability with these dots here, where the different dots correspond with these category choices from better to worse, that's categorical data. And then the percent recommended tested models from the different makes are quantitative, or you can think about it as numerical data. So what are some questions a consumer might answer using this data? You might want to know which overall score range is most popular. You might want to know how many car brands have very good or excellent reliability. So Consumer Reports interprets these predicted reliability circles as, we could say, excellent, and then the top half shade, very good, the middle is good, the bottom half shade is fair, and then the solid dot is poor. So we're going to construct a bar graph for predicted reliability using the counts here. So what I've done is counted up how many of each of the different types of circles, and I've gone ahead and put this in StatCrunch. So over here I've got my predicted reliability categories. I've got excellent, and I counted 2 cars had that, so you can check those values. Very good, that's the top half shaded, I counted 6 cars. Good, I counted 11 cars. Fair, I counted 7, and poor, I counted 4. So we're going to make a bar graph because this is categorical data. Since I've done the counting, when we go to graph, bar plot, we say we're doing this with summary. So my categories are where I type predicted reliability, and my counts are in this column that I call counts. And if we just click compute, we see here's a bar graph. Now, does the order of the bar graph have any meaning here? Look at the order. It's going from excellent to fair to good to poor to very good. So how did StatCrunch decide on this order? Well, StatCrunch alphabetizes by default. So in terms of comparing, you kind of have to look from excellent to good. Oh, and very good's over here. So you can go ahead to Options, Edit, and see how it says Order by Value Ascending? I'm going to choose Order by the Worksheet. And then it leaves it in the order that I had here. Now remember, this is categorical data, so we can arrange it in any way we want. It's not numerical data where there's an ordering. So if you wanted to arrange it from count ascending, then you'd have the smallest count first, which is excellent, and then poor, and then very good, fair, and good. I like it in the order that we had on the worksheet. So I'm going to go back to order by worksheet here. That makes the most sense to me to go down the comparison from excellent to very good to fair to poor. Now in StatCrunch, if you want to save a graph, you can go to Options, Save, and then you can give it a title, bar plot with summary for consumer reports. I have some groups I've created. You don't have to share it with groups. If you want to just keep it for yourself, you say, don't let the public see this result. And then you click Save. And then you can mail it to yourself or you can view it. To find your data when you're back in StatCrunch, if you're back home in StatCrunch, if you go to My StatCrunch and My Data, you'll find all of your data saved in there. And I have quite a lot of different graphs in here, but you would find my data there, or you can also go to My Results. And so here's my bar plot under My Results. And so you've got it always saved here if you want to come back to look at it. So if you draw it by hand, you can sketch this graph from StatCrunch on the grid. And we want to describe what we notice. So let's go back to StatCrunch and see what trends we notice. So we notice that good had the most frequency. If we hover our mouse over, we see that had frequency 11, meaning 11 cars had good predicted reliability. And excellent had the least frequency, with only 2 cars being rated as excellent. All right, here's a mosaic plot. You can read about it in our textbook. There's some other examples in there. This is sometimes known as a Marimekko diagram. And it's a graphical method for visualizing data from 2 or more qualitative variables. So qualitative is another way of saying categorical variables. You'll run into that term. So in a mosaic plot, counts are represented as rectangle areas. So the important part of the diagram to pay attention to is the length of the sides and how the side lengths compare for the variables. So one advantage of a mosaic plot is that you're quickly able to compare 2 categorical variables. So here's a mosaic plot that is titled Older Brothers Are Jerks, and it's constructed from a survey of 3rd grade students in California. So down here on the x-axis, we've got belief in Santa Claus. So this column here is students who believe in Santa Claus, and this is students who do not believe in Santa Claus. Over here on the y-axis, we have older siblings. So we've got the answer choices of having an older sister, an older brother, or no older sibling. And then I'm not sure how they did students who had both an older sister or an older brother. So I don't know how they were counted. Maybe they got 1 vote in each. So what do we notice here if we look at this? So we see that there's a big rectangle, meaning a lot of students who had no belief in Santa Claus also had an older brother. And we see that there's a small rectangle for belief in Santa Claus for students who had an older brother. So what does that mean? Okay, so we know our variables are belief in Santa Claus on the x-axis, existence of, and the gender of the older sibling for the 3rd grade students on the y-axis. So we want to know, is this relationship independent? So is having an older brother independent of whether or not a 3rd grade student believes in Santa Claus? So from this mosaic plot, we see there is a relationship between no belief in Santa Claus and having an older brother. Here's our relationship. The counts, which we see visually as a box here in the rectangle, is much bigger, no belief, for students who have an older brother. And similarly, for students who have no older sibling, no belief is much smaller and belief is much bigger. So since the mosaic plot bars are not equal for each older sibling option, we conclude that belief in Santa Claus does depend on whether a student has an older brother. If belief in Santa Claus was independent, meaning no relationship to whether or not a student had an older sibling, we'd expect all the bars to be equal in both the belief and no belief columns. So since our bars are not even close to equal here, we see there is some sort of relationship. So our conclusion would say that belief in Santa Claus depends on having an older brother or not, right? Students with older brothers have much less belief in Santa Claus. And so that's the title of our graph, Older Brothers Are Jerks. We will now look at displaying quantitative variables, histograms, and stem plots. So when we look at quantitative or numerical variables, we need to be able to see the relationship between the numerical values. And so in a histogram, you're not going to see the names of individual people, but you are going to be able to determine at a glance the counts or the percents of the individuals within each range that we determine. So we're going to look back at that Consumer Reports data for the percent of recommended test models. So we come back a couple pages. Here was our Consumer Reports model, and we had all these percent recommended models corresponding with the number of cars. So this is numerical data, and we're going to do a grouping by percents and see if we notice any trends. So there's one typo here. This should say 80 to 99%. And so I made what we call our bins or our classes, each 20 percentage points wide. So the first bin goes from 0 to 19%. The second bin goes from 20 to 39%. And so you can use the chart to count up the frequencies. And so we see we've got 7 cars from 0 to 19%. You can count 8 cars from 20 to 39%, 3 cars from 40 to 59%, and 6 cars from 60 to 79%. And then from 80 to 99%, we've got 3 cars here. And for 100%, we had 3 cars. So I went ahead and translated this to a histogram. So in a histogram, we've got our percents down here, and then we always count the frequency on the y-axis. So the frequency is the count of how many fall into each of these bins or classes. And so you can see my bars here correspond with my frequency. So the height of the bar corresponds with the frequency. And we look to see, well, is there a relationship? It looks like the peaks are from 0 to 40%. We have a little peak from 60 to 80, and then a shorter bar heights for 80 to 100%. So we would say this looks like, if I draw a curve over it, this looks like it's got what we think of as a right tail, or skewed to the right. So we're going to go look at StatCrunch and see how we can create the same data. So if I'm in StatCrunch here, I'm going to exit out of this graph I made previously. It's not lost. You can go into StatCrunch results and pull back up your bar plot if you want it. So go ahead and exit out of it. And then over in the third column here, I've typed the percent recommended models. And so I'm going to go now graph histogram because it's quantitative data. And notice it only gives me the number columns to choose from. So I'm going to choose percent recommended test model. And if I just go compute, I get a default setting. Now in this case, luckily my default setting corresponds with my bin lengths of 20 that I chose. Notice when I hover over the first bin, it's got frequency 7 because there are 7 cars from 0 to 20. Now notice the 0 has that close bracket with it. That means that this bar includes 0. And notice the 20 has the parentheses. That means 20 is not in this bar. And then if we go up to the next bar and hover our mouse over, we see it was frequency 8. And then the closed bracket on the left tells us 20 is now included in this data all the way up to 40, but 40 has a parenthesis, so we see 40 is included in the next bar. And that's just how we did our bins here in StatCrunch. So we're going to look at what if we tried some different bins here in StatCrunch. So if I want to go to Options Edit, say I wanted my bins to start at 0 and instead be 10 wide. Notice my data is now broken up a little smaller, and we can't quite see the same trends. We still sort of see, if we take our mouse over, the right skew or the right tail relationship. Now if I go all the way down to bin size of, say, 5, we see there's a lot of bins that are just 1 tall, frequency 1. So this is what we start to call pancakes. So you'll notice that our data often says avoid skyscrapers and pancakes. So in our directions, we don't want bins that are just 1 tall like this, because that's not going to tell us a whole lot. Skyscrapers would be if we make our bins too wide. So for example, if I make my bin width 50, I can see the right relationship, the right skew relationship, but I've got pretty wide bins here, and it looks like what we think about as skyscrapers. So I'm going to go back to that bin size 20 that we used. I think that's a good choice. and we see here the same graph. So now let's make a stem plot to compare. So we can go to graph, stem, and leaf plot. So we say stem plot or stem and leaf plot. And we'll do % recommended test model. And then we want to choose the leaf unit. So we want our leaves to count by tens, I think. And if we say compute, we see here we've got, oh, this is tens, meaning this is everything from 0 to 40. This is 50 to 90, and this is 100. So maybe we don't want our leaf unit to be tens. This is looking a little bit like the skyscrapers. So let's go options, edit, and make our leaf unit 1. And now we see we've got all the zeros, all the ones, meaning from the numbers in the tens. So this is telling us there were values that were 17, 2 values that were 17. This 2 now, because our leaf unit is 1s over here, this 2 is a tens place. So this is 20, 25, 25, 25, 27, 29. So when we make a stem plot, our value on the left is 1 place higher than our leaf unit. So if our leaf unit is 1s over here, then these are 10s over here. Here's 33 and 38. So if we go back to making our histogram have bin size 10, because our stems over there are counting by tens, take a look at this. If you do a little side-by-side comparison, imagine rotating your stem plot around and notice the 0 bar here that has frequency 5 corresponds with the 0 stem here that has frequency 5. Now, the 2 values that are 17, we see that in the 10 to 20 bar here. There are 6 values from 20 to 30, and we see that in the 20 stem here. So the stem is 20, meaning here's a value that's 25, here's a value that's 25, here at the end is a value that's 29. So we read each numerical value that way. So what were the similarities or the differences? So when the bin size is different in the stem plot, we notice the shape is still skewed to the right, and you have to rotate your head a little bit. But if you draw the distribution over, we see there's a little bit of a right skew here, and we see the same thing in the histogram. Regardless of whether our bin size is 10 or 20, we see that right skew. So who uses stem plots? Well, if we're graphing by hand, stem plots can be a fast way because you break it down into the digits on the left. So you would count by tens here, and then you would go down your list and say, okay, 100, I'm going to put a 0 here. 88, I'm going to come over here and put an 8. A 60, I'm going to put a 0 over here next to the 6. So if you're working by hand to try to graph and see the distribution of the data, stem plots can be quick ways to do that by hand. In our class, you can either draw your stem plots by hand, or you're welcome to put the data in StatCrunch and let StatCrunch make the stem plots for you.